It turns out that the standard valence bond model that we just discussed can't fully represent the correct structures that we observe in molecules. One obvious example is the difference between the bond angles of H2S and H2O. Both molecules are formed by two hydrogen atoms and one group 6A element, which is oxygen and sulfur. In H2S, which is shown in this picture, applying the valence bond model results in a prediction of a molecule with a 90-degree angle between hydrogen-sulfur hydrogen, which is very much in agreement with the experimental bond angle of 92 degrees. Since oxygen is also a group 6A element, we would expect that the HOH angle in H2O will also be around 90 degrees if we apply the standard valence bond model to water. But the angle is actually 104.5 degrees, which is much closer to the bond angle that we would have observed in tetrahedral structures, which is 109.5. So the difference between these two structures imply that using standard atomic orbitals, the s, the p, the d's, and the f's, is not going to be enough to describe how atoms form chemical bonds. So this discovery is what led Linus Pauling, the same scientist who created the electronegativity ranking of elements, to propose a new set of wave functions for atomic orbitals, which he called hybrid atomic orbitals. So what are these hybrid orbitals? Remember that each atomic orbital is represented mathematically by a wave function. What Pauling proposed is that we can combine these existing atomic wave functions in a process he called hybridization and use these new hybrid orbitals to explain the properties of chemical bonds. So it's important to note that hybrid orbitals are mathematical functions. They're not actual physical objects. However, they're very useful because these functions help us predict the properties of chemical bonds that we observe experimentally. So I'm going to now discuss how hybrid orbitals are created conceptually. There are different types of hybrid orbitals, just like there are different types of standard atomic orbitals. We'll start with the simplest hybrid orbital, which is called the sp hybrid orbital. We'll use the molecule BeCl2 as an example of how these orbitals are formed and then used in bonding. So remember from the Lewis structure discussion that BeCl2 has a linear structure as shown here with a 180-degree bond angle. Be is one of the species that is still stable even though it's electron deficient, meaning that it doesn't have 8 electrons around it. To illustrate its bonding using the valence bond model, we have to look at each element's electron configuration just as we did in prior examples. So when we look at Cl, it's clear that it has one orbital that has a single electron, so it's going to use that 3p orbital for bonding. When you look at Be electron configuration, we don't see any single electrons. But remember that that's a requirement for a bond to form using the valence bond model. So if we just try to use that standard atomic configuration, we're not going to be able to come up with a model for BeCl2 because this configuration would predict that beryllium cannot form any bond with any other atom. This is where the hybrid orbital concept becomes necessary. First off, we know that there's going to be two bonds that beryllium is going to form with the chlorine atoms. So that means we're going to need two single electrons in beryllium for that to happen. So here, Pauling proposed the concept of valence electron promotion. We're going to move one of the electrons from the 2s orbital to a 2p orbital. So now the new configuration looks like this. Once we have this, we can see that the beryllium atom can form two bonds with other atoms because there's two single electrons. But it's not enough to stop here. The reason is because one of the bonds will be a result of a 2s 3p overlap, and the other bond would be a 2p 3p overlap. Because they have different orbitals that make up each bond, we would expect those bonds to be different in BeCl2. In other words, this bond is going to be different than that bond. But experimental measurements show that these two bonds are exactly identical. So that picture alone is not enough. So then Pauling came up with a second step to the hybrid orbital creation, which is what he called hybridization. Hybridization just means he's doing a mathematical operation, and that mathematical operation is called linear combination. And what he's doing doing the linear combination on is the two different wave functions that corresponds to the 2s and the 2p orbitals. Now, what is linear combination? Mathematically, it looks like this equation right here. So the symbol phi sub I represents the result of the linear combinations, the new function or the hybrid orbital function that you will get. Chi1, Chi2, Chi3, and so on represents the individual standard wave functions that we're going to use. In the case of beryllium, the Chi1 will be the wave function for the 2s orbital. The Chi2 would be the wave function of the 2p orbital, and that's it. There's no additional wave function. So that particular linear combination would only have two terms in it. The rest is nothing. C1i and C2i and so on represents the weights that we apply to each function. So for example, if the hybrid orbital is 50, 50, 2s and 2p, we would say this is 50% and that's also 50%. It could also be that this is 20% and that's 80%. So it's just the different types of weights that we apply on the existing wave function to generate our hybrid orbital wave function. The resulting hybrid orbital wave function is then what the beryllium atom uses to make bonding with the chlorine atoms. So let's take a look at what the hybrid orbitals look like that we generate for beryllium. Now, we're not actually going to do the math here, but we're just going to use a graphical representation of the orbitals to help us show how linear combination works. Now, remember that orbitals are mathematical functions that represent waves. So a linear combination operation can be thought of as interference of these waves. There are two types of interference: constructive and destructive. Constructive means you're adding two waves that are in phase, where the trough and the peaks are aligned. Destructive interference means you're adding waves that are not aligned. Now, they can be exactly out of phase, 180 degrees in this case, where the peak corresponds to a trough of the other one, or they can be slightly misaligned. But both of them are ways of adding waves. If we apply this idea to the addition of the orbitals of beryllium, we can say that first, we're adding the 2s with the 2p orbital in phase. Mathematically, it can be shown using this equation, but graphically, it's shown through this addition right here. Now, the s orbital only has one phase, while the p orbital has two phases opposite of each other. So when you add these two together, you're going to get this new wave function that has a larger lobe on one side and a much smaller lobe with the opposite phase on the other side. Now, if we do the out of phase addition, we still have the s as a positive phase, but then now you can see we flip the p here. What you get is this wave function that has a really large lobe on the left side and then a very small lobe on the right side. The name of this hybrid orbitals that we just make is called sp because it's composed of one s orbital and one p orbital. Taking the individual sp orbital and combining them together in one drawing results in this following picture, which is the representation of the sp orbitals for beryllium, with the two lobes oriented 180 degrees apart from each other. Now, this is an important idea because it should alert you to the fact that the BeCl2 bond itself that we have observed experimentally is 180 degrees, meaning that just by using the hybrid orbital concept, we're able to reproduce the experimental observation of the bond angle. The drawing here illustrates the actual valence bond model of the BeCl2 molecule. The central Be atom utilizes its two sp hybrid orbitals, which is colored in purple, each of them containing a single electron, showing with that up spin arrow. Each chlorine atom is using its 3p orbital, shown in green, which also contains a single electron. So each bond in BeCl2 is an overlap between an sp hybrid orbital and a 3p standard atomic orbital. Now, the bonds here are both sigma bonds because they are cylindrically symmetric around the bond axis. Another important point is the presence of the empty p orbitals, which is colored in gray here. Recall that when we did the hybridization of s and p, we only used one s and one p. The other two p orbitals are not hybridized, so they remain in their standard state. You'll see in later examples that these p orbitals can be used to form form pi bonds in certain molecules. Now let's take a look at the energy diagram of these hybrid orbitals. The hybrid orbitals has energy that is somewhere between the 2s and the 2p, which makes sense since it's composed of those two standard atomic orbitals. You may ask why the atom wants to use the hybrid orbitals if there's no advantage to forming them. Well, the reason is because the atom doesn't just form the hybrid orbitals and fills them with the single electron. But the hybrid orbitals is then used for bonding. And it is the bond formation which actually gives the molecule a preference for using the hybrid orbital function as opposed to the standard atomic function. And that's what results in the stabilization of the molecule. And this is an important point because you don't see hybrid orbital used in atoms. You only see them used in atoms that have formed bonds. So that's a clear idea, right? When we talk about quantum mechanics, we only talk about the standard atomic orbitals, the s, the p, the d, and the f. Now, when we talk about those atoms bonding with another atom, that's when we need to introduce the concept of hybrid orbitals. Now, what this also means is that the more bonds you have, the more stable that molecule will be, which also means that the hybrid orbitals are typically only used to explain the bonding for central atoms, because the central atoms are the atoms that have the highest number of bonds. So they have the most reason to use hybrid orbitals in illustrating the way they bond with other atoms. This should be your assumption when you're drawing orbital overlap using the valence bond model. Terminal atoms don't use standard orbitals unless you have many bonds for those terminal atoms. So I want to summarize some key points here about hybrid orbitals. First off, hybrid orbitals are mathematical creation to help explain the properties of atoms and molecules. As a result, hybrid orbitals only exist for atoms that are bonded. They don't exist for isolated atoms. Now, because hybrid orbitals become more stable with increasing number of bonds, hybrid orbitals are typically only used for central atoms. Again, recall how hybrid orbitals are formed. We need to do linear combination on standard atomic orbitals. The number of hybrid atomic orbitals that you make is equal to the number of standard orbitals that you use. So for example, with beryllium, we combine one s orbital with one p orbital, so we end up getting two sp hybrid orbitals. All hybrid orbitals that we make are degenerate. That means they have the same energy. So the two sp orbitals here are degenerate. Overlap of hybrid orbitals result in sigma bonds. You'll see later that pi bonds are only formed by side-to-side overlap of standard orbitals. When we complete the discussion for all the hybrid orbitals, you will see that it's not necessary to go through all these steps that we just did to figure out which hybrid orbitals you should use for a given atom. It turns out that the Lewis structure and VSEPR theory can be used to easily predict what hybrid orbitals will be needed for a given central atom. We'll talk more about that once we finish talking about all the hybrid orbitals. In the next video, I will describe the other hybrid orbitals that you will see in most covalent compounds.